Everybody. So, chapter 2 for physical science is another chapter that is kind of general information that we need just so we can kind of keep on going in science. And we'll get to physics, but we have to get through some of the other stuff first. So, chapter 2 covers matter. And matter is anything that has mass and occupies space. So anything that you can see or feel or sense, if it can be measured, it is matter. Everything in the universe is matter as long as you can measure it or see it, those kinds of things. It can be any size from huge to teeny tiny, and all matter is made up of particles. And we'll talk about different names for particles in a few slides. But for the most part, we're talking about atoms there. So the states of matter, you guys know, are solid, liquid, and gas. Plasma, I have on the list there. It is one that you guys aren't going to, run into as you're walking down the street. This is what the sun and some of the other planets are made up of, but it is only found under really special conditions. All of the states of matter are determined by the arrangement of the particles or the atoms that make them up, and then the motion of those particles. So if you have water, ice has the same exact particles as water. They're just closer together. If you have steam, or water vapor, same exact particles, except they're moving faster and are spread apart. And so it's not the actual molecules themselves or the particles, it's what they are doing and how close together they are. Okay, so the particle model, this was a big deal. Of course, they all are in science, but this was a big deal because it was really an explanation of atoms. Way back in the day, a Greek philosopher named Democritus said that, or came up with a theory that all matter can be divided into smaller and smaller particles until you get to a particle that can't be divided. And he said that this particle, he called this atomus, that's the Greek word. It is where we get our word for atoms. And so you have had this early on idea of atoms. And unfortunately, one of the other philosophers who was a little more famous, Aristotle, disagreed with the concept of atoms, and it was actually forgotten about until the Renaissance, until people started really studying the writings and started doing experiments for themselves. Now, once they got to that point, then they started studying after the Renaissance, and by the mid-19th century, so a long time ago for us, atoms were widely accepted. But originally, they weren't quite so popular. Now, these particles are measured in nanometers, which is really, really tiny. You're talking like the width of a piece of hair kind of a thing. And the most common are atoms. And these are obviously not, you can't see them with your eye, but we do have the ability to see them with a scanning tunneling electron microscope. There's a picture of one there on the page. It is a very, very big piece of machinery. It's nothing like the little microscopes we have in our room, but it has magnets and vacuums and mirrors and all kinds of things. And the images are projected onto a computer screen, and so we can see them, but it is still pretty difficult because of their size. But they are what gives substances their physical property. So if it's a solid or a liquid, or the color, or how it reacts with certain things. And so these particles and how they interact with each other are what determine how the substance behaves. So now the evidence for the particle model, first off, there's constant motion. So we, and those little video links that you see there on the screen, we'll watch those in class. If you're watching this at home, you may want to go to those on your own, but they show what is called Brownian motion. And so Brownian motion was discovered by a guy named Robert Brown, and he was the first to observe this motion. And I think he was looking through a microscope at water with pollen grains in it, and the pollen grains were shaking. And so he realized that there was something in there moving, and he determined that it was actually the water molecules. And then from this, he and other people eventually came up with the kinetic molecular theory that says all matter is made up of tiny particles, and that those particles are in random constant motion. And so we see the process of diffusion kind of based on this constant motion. It's like if you, and we'll probably do this in class, if you put a drop of food coloring into a cup of water and you don't stir it, it won't mix right away, but give it enough time and it will be completely dispersed throughout the water. That's evidence for the motion of these particles. Okay, so now these particles, like I said, mainly we're talking about atoms. And atoms are the basic particle of matter, and everything is made up of millions and millions of atoms. And so the structure is one that is familiar to you. You have a nucleus, which is in the middle. That's the center. And so on our little picture, it is right here in the middle. And so you have protons and neutrons in the nucleus. Protons are positively charged. They're immobile, so there is no movement. They're not going anywhere. They do not leave the atom under normal circumstances. And then you also have in there neutrons. Neutrons have no charge, and they basically are in there to help the protons be close together. And then outside on our little picture there, they're the green. They're following these little loops. These orbits show where the electrons are. And they are in the space around the nucleus, which is called the electron cloud. And they are negative, the negative charge, and they are much, much smaller than the protons or neutrons. The picture has them represented as little dots. But if you had the true representation of the size difference, you wouldn't be able to see the electrons at all. They're so, so small. And normally, or if you have a neutral atom, the number of protons and the number of electrons are equal, so they would cancel each other out. Okay, so molecules. When you have two or more atoms that bond together, they will form molecules. They can be very simple, like two oxygen atoms bonded together, very complex. DNA, which is your genetic material, is a huge, huge molecule with hundreds of atoms that are bonded together. So it's very, it depends on the function of those molecules. Now, also with atoms or with matter, I want you to know what ions are, and that is when a neutral atom gains or loses electrons. Changing the number of electrons means that they no longer match up with the protons, and so you have this mismatch. When you have more electrons, so electrons have been gained, you have what is called an anion. And because there are more electrons, more negative particles or more negative pieces, you have a negative charge. And this negative charge is because of the excess electrons. The other thing that could happen is you lose electrons, and this causes the formation of cations. Now it looks like cations, it's cations. And these cations have fewer electrons than they did, which means their proton number is higher, and that's where you get the positive charge. So, and we'll go over this more, and when we do chemistry next semester, we'll talk about it again. But the one thing I really want you to really remember is this happens when you have the loss of electrons. Electrons are the big thing that we're changing here. Okay, so now classification of matter. Matter is put into two big groups. Pure substances, sometimes I just say substances, and mixtures. A substance is either an element or a compound, and so you have an element where you have only one kind of atom. So if I have a handful of gold, every atom in my hand has the same number of protons. and that is the thing that determines the type of atom or the element that you have. So they all have to be identical as far as the number of protons goes. Compounds are when you have two or more atoms bonded together, but they always have to be the same two in the same ratio. That's this fixed ratio that I have in the definition there. And this fixed ratio means that it always has to be that ratio. For example, water is always H2O. And so I can't change the number of H's, I can't change the number of O's unless I change them proportionately. So for example, if I added an O, if I had H2O2, that's not water anymore, that's hydrogen peroxide. Way different. But if I changed it to H4O2, it's still the same ratio, and so it would still be water. And so it has to be very precise. Mixtures, on the other hand, are pretty random. They're physical combinations of two or more substances. And there are two types of mixtures. You have homogeneous mixtures, and this is where you have different substances that are put together in random amounts, but they appear the same because they are maybe the same size, or the same color or something like that. And basically, it looks the same to your eye. And so, for instance, if you make a glass of Kool-Aid, once you mix the Kool-Aid powder into the water, you can't then pick out water or powder. It's all the same. It mixes so that your eye can't distinguish between the two things. Very often you will hear me refer to a homogeneous mixture as a solution. Okay? Now, the other mixture is heterogeneous. Heterogeneous is when you have particles of different substances and they have very different sizes, different appearance. And so you can actually pick out the different pieces in a heterogeneous mixture. So for example, like trail mix, you have pretzels and peanuts, you have M&Ms if it's the good kind, and all these different things, but you can, in your hand, pick out the things that are different because you can see it. That is heterogeneous. All right, so now changes in matter. These changes are are based on the atomic arrangement, the particle arrangement, and these are the properties, that we are looking for. And so if it is anything that can be seen or measured, we're talking about a property. Sometimes these change with temperature, like the size of something. It can swell or constrict in different temperatures or atmospheric pressure, but it's pretty set. Physical properties. Physical properties are things that you can observe or measure, and you don't really do anything to the actual substance. You don't change it in any way. So I can just look at something and say, okay, that is purple. I can use a scale to weigh something and determine the mass of it. I can calculate the density based on the mass and volume. So I don't do anything other than make some observations and maybe some calculations. So also with physical changes, you're not changing anything. I kind of said this already, I got ahead of myself, but you can change the state. So it can go from a solid to a liquid. So ice and liquid water are the same substance. Okay, remember they're both H2O. And I can get it back. I can put the liquid water in a freezer and I'd get ice back. Form. So if I dissolve sugar in water, I may not be able to see the sugar anymore, but if I let the water evaporate or if I boiled that solution that I made, then I would get the sugar back, so I can get it back. And then the last one is shape. Your book uses the example turning a log into sawdust. Sawdust is still wood. Now, I obviously wouldn't want to spend the time to like glue back together all of the sawdust to make the log. I guess I could if I had a whole bunch of time, but you can get it back or it remains the same. All right, now chemical properties. This is a little more in depth, and so if a substance changes in the presence of another substance, you have determined a chemical property. So if something is flammable, so if it bursts into flame in the presence of fire, then you have determined that it has this chemical property. Corrosiveness, if it works to rust other things, then that's a chemical property. Or if it can be rusted, if it goes through oxidation, that is chemical. Knowing if something is acidic or basic. Alkalinity, this word here, alkalinity is just refers to if something is a base or not. Now, chemical changes, this you actually have an effect on the electron structure of the atoms, like you rearrange the atoms. And so if you get something, a new substance, and you can't get it back to the old substance, then this is a chemical change. Burning things, if you burn a piece of paper, you end up with a bunch of black kind of soot, ash, left over. There's no way that's going back to paper. Rust, you cannot turn that back into smooth steel. Some of it, has corroded or rusted away. All right, so now, conservation of matter. In any of the changes that I just talked about, physical or chemical, the amount of matter before is equal to the amount of matter after. They're rearranged. They may look different. It may feel like some of them are gone. But if you could get everything back, out of the atmosphere, if you've burned something or, whatever it is, and you could add back up all of the atoms that you had, that number would be exactly the same. This is the law of conservation of matter, and it applies from the very beginning. The number of atoms that God made in the beginning are the number of atoms that we have now. We have just over the years rearranged, moved around, put in different arrangements, different places. But if we could gather it all back up and count it out again, that number would match what God put here from the very beginning, which blows my mind personally, but it's true. Okay, now nuclear changes. These are extreme compared to physical and chemical. This is when you change the nucleus of an atom, which requires either being naturally radioactive as a substance or some pretty extreme lab conditions. And this happens when a nucleus either emits or shoots out a proton or a neutron, or it absorbs them. And so you've changed something in the nucleus, and that is huge. Massive amounts of energy are released. It's what the hydrogen bomb, the nuclear bombs that ended World War II were based on. It's a pretty good power source for us, but again, it's not something that just happens. Okay, so now back to easy changes. So changes in state, these are sometimes called phase changes. So if you have a change in the state, you're going from solid, liquid, or gas to one to the other, but the matter stays the same. That's a phase change. And this can be based on temperature. And so increasing the temperature causes the molecules to move faster. So if you are adding heat, you're adding thermal energy, you are increasing that temperature. If you decrease the temperature, the movement of the atoms slows down and they become closer to solid, possibly. And so if you're losing thermal energy, it gets colder. Now, with melting, when something melts, thermal energy is added to a solid substance. So ice is the easiest one, of course, to think about. So ice melting is pretty easy concept for most of us to think about. And so you have this ice sitting out, or you put it in a pan and it's on the stovetop. You heat it up, you're adding thermal energy. The particles begin to just shake. So they're kind of vibrating. You can't see anything happening, but they're moving faster and faster. Eventually, they are able to move so fast that they break away from the other molecules that are around them. And once they're in this liquid state, they're still touching, but it's more kind of a flow of movement instead of, kind of sitting in place. The melting point is when you've reached a temperature where that solid turns into a liquid. Pure substances and mixtures differ in their melting points. A pure substance will have one melting point, and a mixture will have multiple. Freezing is the opposite. This is where you take water and you stick it back in the freezer. And so this is where the liquid loses thermal energy, so it becomes colder. The particles, the atoms that are in there begin to move more slowly. And as they're moving around really, really fast, and they're doing all this stuff, and then they get closer and closer and closer together, and then they're stuck in place. And then they are trapped in this fixed position, and then it's a solid. And so the freezing point, again, like the melting point, is basically where they go from a liquid to a solid. And pure substances, again, have one freezing point. Mixtures will have a melting point that kind of varies. Okay, so now vaporization. This is another phase change. Your book goes into lots of detail on this. They really like vaporization for some reason. So we're in a liquid state to begin with, and the particles are in constant motion, and they're colliding with other particles, so they're just all kind of moving around. It's just chaos. And every time they collide, there is a transfer of energy to one of the particles. So two things hit together, one gets more energy, and so it moves off way faster, and the other one's still moving, but not as fast. Like my big hands in your face right there. And so as more and more collisions happen, eventually some particles will gain enough energy and have enough speed to break away from the other particles if they're near the surface of the liquid, if they have space above them to move away. The particles that have enough energy and that do break away become gases. And so that is vaporization. It's evaporation, essentially. And the rate is how quickly it happens. It depends on the liquid temperature, so how warm the liquid is, and also the vapor pressure. Vapor pressure to us is basically like humidity. So how much liquid is already in the air. The temperature causes the particles to move faster. The vapor pressure basically acts, if there's a lot of it, it acts kind of like a seal over the surface of the water, and so more gas can't get out. Low vapor pressure, there's plenty of space, and then they can escape more easily. Okay, so more vaporization. With vaporization, you have basically two things, two possibilities. You can boil something, and with boiling, you put heat into the liquid, and this causes the particles, the atoms, to move faster. It causes vapor bubbles to form within the liquid, and they start to rise to the top. This picture right here, that's of course boiling, and notice the bubbles in there. Those are the little vapor bubbles, and so they form close to the source of heat. So if it's on a stovetop down at the bottom, and they will rise, and if they have enough energy over time, they will rise all the way to the surface and then break free. Evaporation is what we just described with vaporization, and this occurs at the surface of the liquid, and this is where just those surface molecules, so just right there on the surface, if they have enough energy to escape, then they can. You don't see any vapor bubbles, it doesn't boil, it doesn't do anything, they just escape. Okay, so now more vaporization, for heaven's sake. Sublimation. This is kind of an unusual thing. It doesn't happen a lot, but this is where you change from a solid to a gas, or a gas back to a solid. They use the same word because science is crazy. But in this case, the substance itself has to be kind of unusual in that the particles, the atoms, aren't bonded very closely to begin with. Dry ice, some of you may have played with dry ice. It sublimates at room temperature, so it will turn directly to a gas. Mothballs will sublime. If you store clothing somewhere, you might put mothballs with them. The mothballs won't be there forever. They will eventually sublimate. Okay, finally, last thing, condensation. Oh, excuse me. Condensation is the opposite of vaporization. So now we have vapor pressure or vapor in the air, humidity to us, and when these vapor particles come close to a cool surface, they will lose energy. And so they're a gas at that point, but as they lose energy, they come slower and slower and slower, and they start to clump together with the other gas molecules right there. And if enough of them clump together, they form a liquid. So this is why water beads up on the outside of your glass if it's cold. This is why, like on really cold days, when you breathe out, you breathe smoke. You breathe out water all the time, but when it's cold enough, all of the water molecules you're breathing out clump together, and then you can see it. So that is chapter 2. Thanks, guys.